Welcome to the 10th part of the series of lectures related to the software for filter design named RM. This lecture is about the description of the results for direct bandpass, constant and linearly rising and decreasing group delay approximation, and about bandpass filters with corrected amplitude characteristic while having a proper group delay characteristic. So we will speak about all-pass bandpass constant group delay approximation, linear phase around central frequency, all-pass bandpass linearly rising and decreasing group delay approximation, which is a parabolic phase approximation, and amplitude correction in the bandpass directly of filters with linear phase. All-pass filters may be synthesized to approximate constant group delay around a given frequency. The RM software allows for maximally flat approximation of these type of functions. The user is supposed to supply the filter order, the normalized central frequency, and the required nominal delay. Here is what one gets where two examples are given. The central frequency in both cases, in both examples, is 1 radian per second. The red line is a 6th order filter approximating nominal delay of 20 seconds, while the blue line is again 6th order filter approximating nominal delay of 10 seconds. Since the area under the curve is the same for curve or group delay is the same for both cases, the approximation interval is better, of course, or broader when the nominal delay is lower. At the bottom part of the picture, of the figure, one can see the phase characteristic of this kind of all-pass filters. All-pass filters may be synthesized to approximate linearly varying group delay around a given frequency, or what is the same, parabolic phase. Positive and negative slopes is allowed. The RM software allows for maximally flat approximation of this type of function. The user is supposed to supply the filter order, the normalized central frequency, the required nominal delay, and the value of the slope. Here are three examples where the nominal delay is the same, the slope is the same, but the order of the filter is varied, of course, or since we are speaking about bandpass filters, the order of the polynomial or the transfer function is even. As one can see, further rising of the order of the filter, in this case with this slope, will be practically not produce any gain, since we are reaching the edge of the straight line is reaching 0. Here is another example where the slope of the group delay is negative, so it is decreasing with the rise of frequency, slopes of 5 second squares per radian, 15 and 30 are produced for a 18th order filter. So these are three different filters with the same complexity and same nominal delay, but with different slopes. Having such results, such opportunity, bandpass filters may be synthesized to approximate constant group delay around a given frequency, while in the same time having selective attenuation characteristic. The RM software allows for maximally flat approximation of the group delay around the central frequency of the passband. The user is supposed to supply the filter order, the number of finite zeros on the omega axis, the number of zeros at the origin, the minimum stop band attenuation, and the relative bandwidth of the filter. Here are two solutions presented. We are speaking about two bandpass filters of 24th order exhibiting constant group delay. The red line is related to a filter whose relative bandwidth is 30%, while the blue line is the filter whose relative bandwidth is 20%. K0 denotes the number of zeros at the origin, and Z denotes the number of zeros at the imaginary axis, and BW is the relative bandwidth. As one can see, the width of the bandwidth and the nominal delay of the filter are interrelated, and the nominal delay is used to control the width of the bandwidth during the synthesis process. It is important to have in mind the influence of the number of zeros in the origin, since they seriously affect the symmetry of the amplitude characteristic. Here ends the 10th lecture of the series. Thank you for your attention.